Let's look at the next type of question where we use a weak acid with an acid dissociation constant, an equilibrium constant for an acid. So a weak acid has an equilibrium constant or an acid dissociation constant because a weak acid is not completely dissociated into H plus ions. It doesn't break up fully into H plus ions, and so this Ka, this acid dissociation constant, tells you how much of it's broken up and how much of it's not. So you need to remember that a weak acid has got an equilibrium constant, and we can also use H plus squared as well for a weak acid and an acid dissociation constant. Let's have a look at this kind of question then. So write an expression for the acid dissociation constant of ethanoic acid. Well, we know that ethanoic acid is CH3COOH, and when any acid dissociates it makes H plus, and whatever's left over, CH3COO minus. So that's the acid dissociation constant that makes these two things divided by the concentration of the ethanoic acid. Ka, acid dissociation constant for ethanoic acid, is 1.74 times 10 to the minus 5. That's that value there. We also know, by the way, that it equals 1.74 times 10 to the minus 5, which is this value there. It equals this. And I've simplified it. So these two things here, CH3COO minus, which is called an ethanoate ion, and H plus, because these are made in equal amounts, because when one mole of ethanoic acid dissociates, it makes 1 mole of this and 1 mole of this. These two are in similar amounts, so I can simplify these two into H plus squared. That's where my H plus squared comes in for an acid dissociation constant. And then that simplifies things. So this value here, the acid dissociation constant, 1.74 times 10 to the minus 5, equals now H plus squared divided by the concentration of ethanoic acid, which is given in the question, 0.136. I multiply this value here by this value here, and H plus squared therefore equals 0.000174, or 1.74 times 10 to the minus 5, multiplied by 0.136, and it equals this value here. If I square root it, I get the value of H plus, which equals 0.00154. I've actually not finished off the question here. The pH, calculate the pH, so if I've got H plus, I minus log to the base 10 of it, and it will give me the pH. Ethanoic acid, Ka, we've done that once already. Calculate the pH of 0.154 solution of ethanoic acid. Well, same kind of thing. We've got the acid dissociation constant, 1.74 times 10 to the minus 5 is this value here. I've simplified these two things to make it H plus squared, because 1 mole of CH3COO minus ethanoate ions is made at the same time as 1 mole of H plus ions when 1 mole of CH3COOH ethanoic acid dissociates. So I've simplified that into H plus squared divided by the concentration 0.154 of the ethanoic acid. Multiply these two values together and you get H plus squared. So H plus squared is 0.000175 multiplied by 0.154. And I've missed out a step here. If I square root it, I end up with H plus is the square root of those two things, and it equals 0.00164. To turn H plus into pH, I minus log 10 to the base 10 of that, and it will come out as 2.78, which seems to be a reasonable pH for ethanoic acid. HX doesn't exist. Weak monobasic acid means it's not a superacid like sulfuric acid. 1 mole of this reacts with 1 mole of a base. Sometimes they use HA instead of HX. Neither of them exist, but what we do know is that HX makes H plus and X minus, because all acids make H plus, so we must end up with X minus as a product as well. So Ka equals H plus X minus, that's what's made, divided by HX. If they'd used HA as a fictitious acid instead, it would have been H plus concentration multiplied by A minus concentration divided by HA. So it's just a letter there that doesn't really exist. It's not a real acid. They've used X, they could have used A instead. Right, the pH. They've given you a pH. Now that's interesting. They've given you a pH. Why would they give you the pH? Well, the only reason they give you pH is 2.79 is if they wanted to use this. That should be a 9 there rather than a 2.78. 2.79. 2.79 is minus log to the base 10 of H plus concentration. To get rid of minus log to the base 10 of using your calculator, you need to get rid of that minus. So you make this side minus, and then you change the sign minus to a plus. So you swap the signs on each side. So minus 2.78 equals log 10 of H plus concentration. If you inverse log or second function log on your calculator minus 2.78, you find that H plus concentration equals 0.00162. Now then, we know that Ka is these two, H plus and X minus divided by HA. We know that we can simplify this into H plus squared divided by HX. So we're given HX? Yes, we are. 0.085. So H plus squared equals H plus squared divided by 0.085. Now this time we've got H plus. So H plus squared is 0.00162 times itself multiplied by itself divided by 0.85, because we're actually working out Ka. So we're actually asked to work out Ka this time. So you've worked out H plus, you're given X in the question, you divide the two, so this H plus squared divided by 0.085, and it gives you Ka 3.09 times 10 to the minus 5. HCOO minus, write an equation for the dissociation. Well, HCOO, H will make HCOO minus and H plus. Dissociation constant, the concentrations of these divided by the concentration of HCOO, H. The equilibrium constant for methanoic acid is this, so this value equals 1.78. I can simplify these to make H plus squared. So 0.00178 equals HCOO minus H plus divided by HCOOH, which is this here. But I can simplify these two because they're made in equal amounts. When one HCOOH, 1 mole of this dissociates, it makes 1 mole of this and 1 mole of this. So these are in equal amounts. So I can simplify that to H plus squared. So have I got HCOOH? Have I got the concentration of that? Yes, I have. There it is, 0.058. So 0.00178 equals H plus squared divided by 0.0056 rather, sorry. So if I multiply 0.00178 by 0.056, I get H plus squared. Square root it, it equals 0.00316. pH is the minus log to the base 10 of the H plus concentration, and it equals 2.5.